Theme 1, Programming 1.1, Understand the process for the preparation of an architectural program. Programming is considered to be pre-design work which goes beyond the traditional basic services as defined in Document 6. Thus, they must be considered additional services, and fees should be increased accordingly. 1.1.1 Identify the components of an architectural program. The components of an architectural program or functional program, design brief, or facilities program include client's philosophy, values, goals, and desired aesthetics. A description of the services that are to be provided by the new facility. Identifying how the services will be delivered. Identifying the activities, workload, throughput, and other measurements that may have an impact on space. Identifying a number of people and/or staff required to provide the services and all other occupants. Identifying major equipment used in the provision of services. Identifying relationships between spaces or groups of spaces. Preparing detailed space requirements. Using bubble diagrams or flow charts. Determining the overall project implementation schedule. Preparation of preliminary financial information and budgets. Identification of the project delivery method. Identification of regulatory issues such as zoning, authorities having jurisdiction, community plus environmental factors, site evaluation, and/or determination. Identifying site requirements such as parking, circulation, and orientation. 1.1.2 Describe the different process phases for the development of an architectural program. 1. To prepare a functional program in consultation with the client. Architects will usually identify, research, and observe theaters of the proposed building and their work activities, including function by function, room by room, or department by department activity plans, staffing plans, storage requirements, previous precedents, and similar building types, the volume of activity plan for specific facility components such as throughput, amount of material put through a manufacturing process, flow patterns, and human activities too. With this information, the architect can then develop approximate floor areas and technical requirements for the proposed facility, including details of the space or of the workstation, special furniture configurations, environmental criteria, security requirements. 3. Afterward, the architect may advise the client on alternative approaches, architectural and financial implications of various building options. Future requirements, assess advantages or benefits versus the disadvantages or costs of each alternative, analyzed differently. The various steps may appear as such. 1. Establishing goals as to what the client wants and why. 2. Collecting and analyzing facts such as existing site conditions. 3. Uncovering and testing concepts, as in the development of design concepts. 4. Determining needs, creating a balance between the desires of the client and available budget wants versus needs. 1.2.1 Analyze an architectural program regarding its feasibility, project constraints, and opportunities. Regarding the feasibility of an architectural program, one must first consider functional elements, identify the scope of a project, determine the compatibility of a program with a site and/or new facility, existing or renovated building, explore alternatives such as various site alternatives relative to programmatic requirements, evaluate existing facilities for functional adaptability with regards to the building envelope, mechanical, electrical, and structural systems, as well as code compliance, followed by the consideration of economic elements. Financial studies identifying capital, operating, and maintenance costs, value off the site, real estate market value of project, demographic studies predicting demands and trends, followed by the consideration of regulatory elements, studies off regulations to determine code and zoning constraints, urban design objectives, and community issues related to the project. environmental issues with regards to conservation authorities, heritage and community organizations, followed by the consideration of alternatives, evaluation of potential sites, explorations of alternate construction delivery methods, structural systems, or consultant sources. Analyzed differently, the four major considerations regarding the feasibility of an architectural program are: 1. Form, as it relates to site, the physical and psychological environment of the building, and the quality of construction. 2. Function, as it relates to people, activities, and the relationships between the two. 3. Economy, as it relates to capital, the initial cost of the facility, operating costs, and life cycle costs. 4. Time, as it relates to ideas of the past, present, and future in the context of the previous three considerations. Tasks in this stage involve planning and evaluation to establish parameters, objectives, and expectations of the project, and to prepare the background information and conditions in which a project can be designed and built. Mastering the business of architecture. Feasibility studies analyze and establish economic factors, functional factors, regulatory factors, alternative options, construction methods. Life cycle analysis reports 1.2.2 analyze the program regarding the site components. Regarding the site components, as they relate to the program, one must evaluate the existing or potential site in relation to the building program, budget, and schedule. Some factors to consider are existing site conditions such as solar orientation, prevailing winds, and climate, topography, including site contours, drainage, visual characteristics, physical features, water bodies, etc., environmental hazards, geotechnical and soil information, immediate surroundings, including neighboring structures, shading and solar access, noise, views, and vistas. Property description, legal description, including boundary survey, easements, rights-of-way, etc., vehicular and pedestrian access, utilities and services available to the site. Cultural factors such as site history and historical land use, as well as land value. In preparing a program relative to a proposed budget, determining needs in the process balances the desires of the client against the available budget or establishes a budget based on the defined goals and needs. Wants have to be separated from needs if the program doesn't fit the budget, as most clients want more than they can afford. Clear statements and true needs are required early in the pre-design stage to avoid problems later. One or more of the four elements, form, function, time, and budget, may have to be adjusted to balance needs and available resources. Preparing an outline specification may help in generating an elemental estimate, comparing building typology versus unit costs. 1.2.4 Compare program with the client's objectives. In preparing a program relative to the client's objectives, establishing goals is a useful exercise, as goals indicate what the client wants to achieve. Goals are important to identify because they establish the direction of programmatic concepts, which ultimately suggest the physical means of achieving the goals. It is not enough to simply list the types of spaces and required areas that the client needs. The goal is to list and describe the spaces so that the spaces may be related to an objective. 1.3 Understand the principles of sustainable development within an architectural program. 1.3.1 Describe the principles of sustainable development. The principles of sustainable development seeks to meet the needs of a functional program with respect to material allocation, building orientation, efficiency of building systems, consideration of future uses, and amelioration of the health of occupants through environmental, social, and economic motives, without compromising the ability of future generations to meet their own needs. This is expanded upon in Objective 7.1.5. 1.3.2 Identify optimal site design, as expanded in Objective 7.1. 5. The following factors should be considered: site selection, urban redevelopment, brownfield redevelopment, transportation issues, site impacts, erosion and sediment control, heat islands, site water systems management, light pollution for aesthetic and economic, as well as ecological reasons. The general intent in developing a site should be to minimize the disturbance of existing landforms and features while taking advantage of natural ground slopes and the microclimate of the site. Site development and construction should minimize disrupting the natural drainage patterns of the site and adjacent properties. When modifying landforms, include provisions for the drainage of surface water and groundwater. Attempt to equalize the amount of cut and fill required for construction of a foundation and site development. Avoid building on steep slopes subject to erosion or slides. Wetlands and other wildlife habitats may require protection and limit the buildable area of a site. Take note of building restrictions on sites located near a floodplain. 2.1 Understand the principles related to the siting of a building and its environment. Land planning, urban design, and environmental evaluation. 2.1.1 Describe the physical, cultural, and regulatory factors related to site planning. The physical factors related to site planning. Climate. Prevailing winds, solar orientation, temperature, humidity, precipitation, topographical. Legal description, property limits, easements, right of way, existing circulation and streets, existing vegetation, surface drainage. Geotechnical. Soil type, rock, seismic conditions, environmental hazards, utilities. Sewers, electrical, fiber, optic water supply. Site context, services. Fire and police protection, trash and garbage removal, snow removal. The cultural factors related to site planning. Site history. Former site uses, history of existing structures. Land use. Ownership and control, present zoning, adjacent land, use, type of land, ownership, location, and type of community services. Economic value. Land cost, size of surrounding lots. The regulatory factors related to site planning. Zoning codes, permitted uses, maximum site area, building height, limit, setbacks, parking, landscapes, sight lines, signage, site plan review, lot requirements, street requirements, drainage, parks, other codes and regulations. Historic preservation, site-related items in the code, such as building separation, parking and disability access and service, and emergency access. 2.1.2 Explain urban design issues and planning processes that influence the design of a building on a specific site. Architects need to be sensitive to the existing fabric of a neighborhood that may influence how a project is designed and the impact that the project may have on its surroundings. Ballast. Chapter 2. Site development must be sensitive to the existing neighborhood by respecting pedestrian paths, maintaining size and scale of surrounding buildings, using similar or compatible materials, not creating uses that conflict with the surroundings, respecting views and access to important buildings, trying to fit within the general structure of the district. Respect public facilities such as schools, churches, shops as their location within a neighborhood affect how a site is developed, i.e. maintaining easy access to public facilities, maintaining views, or enhancing their prominence on the street. Wind patterns and solar patterns. Understand how the new building impacts both. Consider how effective urban design will help to counteract suburban sprawl. 2.1.3 Identify strategies for dealing with environmental issues in site evaluation. Strategies for dealing with environmental issues in site evaluation involve the consideration of 1. The larger context of surrounding communities and the urban setting. See theme 2.1.2. 2. The immediate site as it relates to ecological considerations, the impact of construction on the surrounding natural environment, including air, water, land, and wildlife. 3. In urban settings, one must analyze the relationship of the building to its users and the surrounding environment, the impact of this relationship on artificial systems rather than natural ecosystems, the reduction of the burden on city infrastructure, minimization of light and noise pollution and other detrimental pollutants, the building placement, which should avoid undesirable wind conditions, either on site or around nearby buildings, How to ensure that the new building isn't blocking the sunlight from adjacent buildings. 4. In rural settings, the concern must focus on the impact on natural landforms as they relate to irrigation and natural cycles, the impact on water runoff, the impact on wildlife and existing vegetation, the additional runoff from the roof and pavement, which should not exceed the capacity of existing drainage paths, avoidance of disturbing existing ecological systems of plants and wildlife, erosion and sediment control by soil stabilization, which may require seeding, mulching, or structural control methods using earth dikes, silt fencing, and sediment traps. 5. Stormwater management, involving the possible provision of vegetated filter strips and grass swales, bioretention basins and sediment traps. Bios will ESTO provide for water filtration, porous pavement to control rainwater accumulation, exfiltration basins and trenches, dry ponds and wet pond systems, green roofs, shade providing surfaces, minimize footprints, reflective surfaces with high albedo materials which absorb less heat, underground parking areas. 7. Light pollution reduction using shielded lights and increased cutoff angles. 8. Avoid building in areas reserved for agriculture and forestry, previously undeveloped land, areas lower than 5 feet below the 100-year floodplain, areas within 100 feet of wetlands, areas within public park lands, and any ecologically sensitive lands. 2.2 apply the principles related to the siting of a building to its environment. 2.2.1 formulate a building siting solution given a specific site, selected physical factors, and design criteria. 2.2.2 explain the principles of grading and stormwater management as they apply to site design. Grading, respecting the natural contours of the land, is important economically and ecologically. Ideally, cut and fill techniques should cancel each other out. Minimizing the disturbance of the site reduces erosion and controls sediment contamination. Excavation, grading, and removal of existing vegetation can cause serious erosion problems, degrade the ecological and geotechnical balance of the property, and contaminate ground and surface water. 1. Can minimize disturbing existing vegetation and reduce soil runoff during construction with an erosion and sediment control plan. Soil stabilization can be achieved by various planting techniques such as temporary or permanent seeding and/or mulching. Structural control, synthetic controls, can be achieved by providing earth dikes, silt fences, sediment traps, and basin. Stormwater management, respect existing watersheds on site and on surrounding waterways and areas. If modification of existing grades is required, one needs to ensure that adjacent properties are not disturbed. Keep your water on your own property. Runoff is understood as the total precipitation not absorbed into the ground. If the site's runoff is increased due to a roof or pavement, or if the runoff is more than the capacity of the natural or artificial drainage from the site, holding ponds must be constructed to temporarily collect site runoff and release it at a controlled rate. Rainwater collectors can be used to collect water for reuse as irrigation or flushing toilets. Stormwater, collected and transported off-site via storm sewers, create negative impacts on the natural water cycle. This runoff removes water which would normally be infiltrated through the ground surface or deplete through evaporation. A. Lack of infiltration leads to the depletion and degradation of marine ecosystems, lowered water tables, and shrinks aquifers. Allow on-site infiltration and absorption in order to protect the watershed and use green roofs. Stormwater runoff also contributes to off-site water pollution and puts more pressure on city infrastructure systems. 2.2.3 describe the relationship between energy consumption and site design. Architects work with design teams to reduce the amount of purchased energy, such as electricity, oil, and its derivatives, to reduce operating costs and dependence on fossil fuels. Buildings can be oriented and designed to be energy efficient. Optimum building orientation is achieved with a rectangular building oriented with the long direction set east-west to minimize intense solar radiation, while taking advantage of the heating potential of south-facing surfaces in winter. The angle varies depending on the climactic region: 12 degrees in cool climates, 17.5 degrees in temperate climates, 25 degrees in hot, arid climates, and 5 degrees in hot, humid climates. The siting of a building takes advantage of local condition and uses the sun, wind, and natural features to the advantage of the building design and economy. Long, thin buildings are good for solar heating and make it easier to capture prevailing winds for natural ventilation and daylight utilization. The building shape can affect energy use quite significantly. Thermal loads, heating and cooling, depend on the conductance of areas of walls and roof. Any building that minimizes the total area exposed will acquire less energy. This method works best in colder climates, often in cooperation with sloped roofs and tree cover. Evergreens, especially on the north and west sides, to protect from winter winds. A cubic building has the least amount of surface for the volume contained. A sphere is best, but not a practical shape for living arrangements. Therefore, a two-story building is better at energy conservation than a one-story building of the same GFA. In temperate climates are usually hot in the summer, cold in the winter. An elongated building shape in the east-west direction can take advantage of winter solar gain, daylighting, and minimum heat gain in summer months. Such a house typically has a porch on the south or similar light shelves or overhangs to protect from the sun. Deciduous trees may be planted to the south. In hot, humid climates, an elongated house in the east-west direction allows breezes to provide natural cooling with open courtyards and broad overhangs for sun protection to minimize severe heat gain from the east and west. In hot, arid climates, a more square-shaped building with an open courtyard is appropriate. The use of high thermal mass, due to large diurnal swings in temperature between daytime and nighttime, is useful. In such a scenario, the house is open to the inner courtyard but closed off to the outside. Site selection should give preference to urban sites adjacent to public transit. One must observe adjacency to public transit, areas prone to fire, erosion or landslides, sloped sites that disturb ecosystems, prime agricultural lands used for crops, or indigenous wildlife, solar orientation and wind patterns built with the long axis oriented east-west and fenestration on the south for solar harvesting control, landscaping including coniferous trees on the south and west to reduce summertime solar gain, alternative transportation. Select sites near facilities that allow for transportation options. Reduced site disturbance, conserve natural areas, and minimize building footprints. Stormwater management. Reduce disturbance to natural watercourses by preventing in-site filtration of contaminants, preventing them from entering local waterways, using bioswales with vegetated wetlands, reducing a number of impermeable surfaces, encouraging groundwater recharging, ecologically sensitive landscaping, plant indigenous materials, encourage efficient irrigation technologies, locate trees and plants over dark surfaces to reduce the heat island effect, reduce light pollution, don't pass the property line with lighting, don't shine line into the atmosphere, use light shields, open space preservation, promote infill development and mixed uses, promote development that protects and buffers natural resources, establish procedures that ensure the ongoing management of natural areas. Social factors, density, infill and sustainable communities and neighborhoods, diversity in demographics, transportation accessibility, utilities and infrastructures, economic factors, land value, market conditions, capital, profit-oriented use, or investment. With respect to landscaping, Trees and shrubs must be located to maximize the energy efficiency of a building, i.e. protecting the north wall with conifers to stop the cold wind. This can reduce the heat load in half. Deciduous trees on the south side of a building provide summer shading, while allowing for wintertime solar radiation to heat and light the interior of a building. A row of trees can decrease wind velocity by 30 to 40% at a distance of 5 times the height of the trees. With respect to building shading, the technique must be used selectively to minimize unwanted solar heat gain in summer months while maximizing heat gain in winter months. One can use deciduous trees or shading devices. The orientation of a building facade determines the most effective type of shading device. Buildings are connected to their surroundings. The construction operation and deconstruction of buildings can have negative effects on local and regional ecosystems and watersheds. Conventional practices must be modified to reverse current building life cycle processes that degrade the environment, with the understanding that building can contribute positively to their surroundings, environmentally and socially, as well as economically. A building can be an attribute to a community by providing certain services and utilities, as well as establishing intrinsic aesthetic, urban, and social values. 2.2.4 describe the impacts of universal accessibility as it applies to site design. More transit accessibility from a transportation element into the building. Use a barrier-free path of travel to the main entrance, including an accessible route from the sidewalk or roadway and parking area to the building entrance. Exterior ramps of a slope of not more than 1 in 10. Parking areas must have a minimum number of designated parking spots, such as 1 per 100 spots with a dimension of 2400 mmx 1500 mm. Access to the parking area must be via a walkway of at least 1,100 millimeters width. Slopes of 112 maximum. Marked crossings at vehicular roadways. Clear floor spaces at accessible elements. Accessible. Ramps where necessary. Curbs with curb-cut slopes. Elevators, floor surfaces, slip-resistant surfaces. Avoid the use of stairs. 2.3 Analyze data relevant to the siting of a building to its environment. 2.3.1 Explain data from environmental and engineering reports to determine design opportunities or constraints. Geotechnical and soil assessment reports are used by the structural engineer to determine the foundation system and structural systems. Refer to Objective 8.3.1. The surveyor illustrates existing natural and built features of a site, while the architect describes the proposed construction in relation to these existing features. 2.3.2 Explain data from a legal land survey. A legal land survey and site plan should include name and address of the property owner and that of the property, source and date of land survey, description of site boundaries, dimension of the property line with bearing relative to north, including angles and curves, a north arrow and drawing scale, the location and description of benchmarks which establish the reference points for the locations of elevations, identification and dimensions of adjacent streets and public rights of way, the location and dimension of easements that cross the site, the dimension of setbacks required by zoning, the location and site of existing and proposed structures, the location and dimension of existing and proposed walkways, driveways, parking areas, and fire access routes, the location of existing utilities, water mains, sanitary and storm sewers, gas lines, electrical power lines, telephone and cable lines, fire hydrants, and proposed points of connection to these infrastructures, existing contour lines and finish grades, planting features, existing and proposed, existing water features, drainage swales, creeks, ponds, floodplains, watersheds, and shorelines, proposed landscape features. The legal description of a site consists of the location and boundaries of a specific parcel of land based on a METES and bound survey, which calls out the course and length of each boundary line of a parcel of land. The survey plot is a legal document describing the location, boundaries, and dimensions of a tract or parcel of land, including zoning and planning commission approvals, restrictions, and easements, the dividing line of streets, block, and lots, and the numbering and dimensions of each lot. 2.3.3 Compare design solutions based on given criteria. Theme 3, Coordinating engineering systems, structural, mechanical, electrical, civil. 3.1 Understand engineering systems. 3.1.1 Describe the main properties of a structural system. The structural system of a building is designed and constructed to support and transmit applied loads safely to the ground without exceeding the allowable stresses in its members, Ching, ch2. The superstructure is the vertical extension of a building above a foundation. The substructure is the underlying structure forming the foundation of a building. Columns, beams, and load-bearing walls support the floor and roof structures. 3.1.2 Describe the main properties of a mechanical system, conveyance equipment, fire suppression, plumbing, HVAC. The mechanical system of a building provides and distributes the essential services to a building for comfort and safety, Ching, ch11. A water supply system provides potable water for human consumption and sanitation. A sewage disposal system removes fluid waste and organic matter from a building. Heating, ventilation, and air conditioning systems condition interior spaces of a building for environmental comfort. Fire suppression systems detect and extinguish fire. Vertical transportation conveyance systems carry people and goods from one level to another in buildings. 3.1.3 Describe the main properties of the electrical system, lighting, supply and distribution, security, fire alarms, communications. The electrical system controls, meters, and protects the electrical power supply to a building and distributes it in a safe manner in order to provide power for lighting, security, communication systems, and various other appliances. A system can be defined as an assembly of interrelated or interdependent parts forming a more complex and unified whole, service a common purpose. A building is the physical embodiment of a number of systems and subsystems that must be necessarily related, coordinated, and integrated with each other, as well as with the three-dimensional form and spatial organization of the building as a whole. The following should be considered when designing various systems: performance requirements, compatibility, safety, control, life cycle assessments, aesthetic qualities, regulatory constraints, economic considerations, environmental impact, construction practices, tolerances, construction schedule, safety, industry standards, division of labor and work. Model codes 3.1.4 describe the main properties of the civil engineering system, drainage, water supply, and infrastructure. Civil engineering systems apply to infrastructural elements that lie between the property line and within 3 feet of the outside face of a building. These systems deal with management of water and drainage discharge, soil grading with respect to topographical stormwater management, infrastructural connections to potable water, gas, telephone lines, sanitary sewers, fire protection services, and storm drainage, surface and subsurface. 3.1.5 lists the codes, regulations, and standards that apply to the engineering systems. Model codes, developed by national organizations which establish standards for structural design, wall construction, floor and roof construction, fire protection, natural light and ventilation, accessibility, and energy efficiency. There are 3 major model codes: the National Building Code, the Uniform Building Code, the Standard Building Code. Companion codes, codes that deal with mechanical and electrical systems. NBC Part 4, Structural Design. NBC Part 6, HVAC. NBC Part 7, Plumbing, Electrical Code. Part 3, Canadian Electrical Code, as well as the following codes: Ontario Building Code, National Plumbing Code, National Fire Code, which deals with firefighting safety and property protection, and the following companion codes: Model National Energy Code of Canada, dealing with energy efficiency, National Electrical Code, Life Safety Code, Fire Protection and Prevention Act, Occupational Health and Safety Act, Heritage Act, Reference Standards, ISO, International Standards Organization, CGSB, Canadian General Standards Association, CSA, Canadian Standards Association, ULC, Underwriters Laboratory of Canada, WHMS, Workplace Hazardous Materials Information System, ENSI, American National Standards Institute, SHRA, American Society of Heating, Refrigerating and Air Conditioning Engineers, ASTM, American Society for Testing and Materials, EPA, Environmental Protection Agency, NFPA, National Fire Protection Agency. 3.2 Analyze engineering systems and their impacts on the project. 3.2.1 Compare the advantages and limitations of the structural system. Advantages and limitations of various structural systems according to material. Wood, types of systems, joists, spans of up to 25 foot, beams 10 to 20, glulam, spans of 15 to 60. Advantages: renewable resource if properly harvested, common and easily constructed, strong in both tension and compression, loads are transmitted in one direction. Disadvantages: combustible construction, except for heavy timber, though limited span 25 foot, defects and limited strength, subjecto, creep steel, types of systems, beam and girder, spans of 25 feet minus 40 inches, open web steel joists, spans of 60, and long span OWSJ, 96 feet minus 144 inches. OWSJs are efficient structural members, well suited for low-rise construction where overall depth of floor ceiling isn't critical. Advantages: high strength in tension, large spans, ductile, availability limitations. Concrete, types of systems of cast-in-place slabs, one-way, beams and girders, spans between 15 foot and 30, and concrete joist systems, spans between 20 feet minus 30 inches, two-way, flat plate, spans of 25, flat slab, spans of 30, and waffle slab, spans of up to 40. Precast structural elements, using hollow core slabs, precast columns and beams, or single or double T-beams. Advantages: good in compression, sustainable when used with fly ash, good thermal mass capabilities. Limitations: weak in tension unless pre-stressed or post-tensioned. Subjecto creep, needs formwork to be assembled when using the cast-in-place method. Masonry, types of systems include single or double rows and cavity-type assemblies. Advantages: high compressive strength, good passive solar energy application. Limitations: limitetto bearing walls, weak in tension and bending, thick walls. The selection of a system must be based upon and or informed by performance requirements, compatibility, safety, controllability, life cycle assessment, aesthetics, environmental impact, relationship with other building systems, construction practices, safety, time constraints, model codes and regulatory restrictions. 3.2.2 Compare the advantages and limitations of the mechanical systems, distribution systems, air, water, and electrical systems, all air systems, constant volume single duct system, residential, high velocity dual duct system, multi-tenant hotels, VAV, variable air volume, constant temperature, most common in office buildings, cheaper than a fan coil system, constant volume single duct with reheat control humidity, multi-zone system, similar to dual duct system, but fewer ducts, useful in square buildings, maximum of 8 zones. DX systems, direct expansion, self-contained individual units, non-duct placed in windows, typically used where ducting is too expensive, and each zone has a separate bill. Air-water systems, fan coils, constant air supply, variable temperature, the most efficient system, used in office buildings where air is pumped through fan coils using water to heat or cool. has a smaller air handling unit and smaller ducts than a VAV system. Induction systems for hospitals and labs where return air cannot be recirculated, 100% outside air, similar to a fan coil. All water systems, often a baseboard heater or radiator, so it cannot control humidity. Single supply and return pipe system, the distance of the pipe is limited. Typically, a two-pipe or parallel system, separate supply and return pipes, if simultaneous heating and cooling is required. A four-pipe system must be used, which is the most common all-water system. Very efficient system. High initial cost. The heat pump removes heat from circulated water and adds it to the air blown into the room for heating, or removes heat from the zone and adds it to the water for cooling. Selection of a system. Performance and cost should be taken into consideration, as well as the following: the building profile, use, and occupancy. The building scale, control requirements, fuel costs, and availability, climactic zone, integration with building systems and structure, required flexibility, economics, sustainability and energy efficiency, energy conservation. Note that HVAC systems in buildings take up 40 to 60% of the overall building energy consumption. 1. Use energy-efficient equipment. 2. Use passive techniques where possible, including, for cooling, natural ventilation, high-mass cooling, earth shelters, roof ponds, evaporative cooling, shading devices, orientation materials for heating, direct gain, trombe walls, water walls, and other mass walls, solar collectors, wind turbines. Geothermal sourcing can also be used to cool via a heat pump. Cogeneration using on-site systems using renewable energy. 3. Mechanical techniques to reduce reliance on HVAC systems. Economizer cycles, which reduces energy required for refrigeration. Dual condenser chillers, solar-powered absorption cooler, based on a natural cycle. Direct contact water heaters, hot water on demand. Heat transfer methods such as the use of heat exchangers, energy transfer wheels. 4. Building automation systems. 5. Commissioning factors to consider when selecting an HVAC system. Performance efficiency, cost, initial cost, and life cycle cost. Fuel, power, air, and water requirements and the means for their delivery and storage. Flexibility of the system to serve different building zones and different demands due to use or site orientation, i.e. decentralized or local systems are economical to install and require short distribution runs and allow each space or zone to have individual temperature control, while central systems are more energy efficient, easier to service, and offer better control of air quality. The type and layout of the distribution system used for heating and cooling media. Space requirements for the mechanical equipment and distribution systems, i.e. air duct systems require more space than pipes for water system or wiring for electrical heating. Integration with the structure, especially with ductwork and weight. Access required for service and maintenance. Construction requirements. Enclosure, fire resistance, noise, and vibration control. 3.3 Coordinate engineering systems documentation. 3.3.1 Describe ways to coordinate with the consultants. Coordination with consultants is generally achieved through communications, meetings, drawings, early planning and input, performance monitoring, and standardization of requirements. Specifically, Document 9, Standard Agreement between architect and consultants, not a standalone agreement. It has to be appended to the prime agreement. Document 6 is a useful device with which to coordinate with consultants. It ensures that consultants have a full understanding of the expected and required services and an understanding of the fee structure for services. In pre-design and budgeting, start the coordination with a teaming session at project inception. Let all the players get to know each other through an integrated design process. It's helpful to involve certain consultants early in project planning and budgeting prior to commencing design work. Ideally, consultants should be involved in every stage from SD, DD, CD, bidding and negotiating, contract administration, and post-construction, including warranty review. Communication is a key factor. It provides ways of coordinating the project via meetings, telephone, email, fax, memos, record keeping, such as meeting minutes, project tracking, tracking of correspondence, and organization of project files. Coordinate through a schedule. A schedule is a planning tool to help organize and coordinate different tasks and timelines, as in CPM. 3.3.2 Identify the key stages at which coordination should occur. The key stages at which coordination should occur are as follows. Pre-agreement. Fee insurance liabilities. Meet client requirements. Pre-design. Confirm the budget and schedule and establish program. Schematic design. View site information and site codes. Structural, mechanical, electrical, civil landscape design principles. View program and space requirements for systems. Obtain space and location requirements and schedule. Discuss best sustainable practices for building systems. Obtain space and location requirements for systems. Obtain estimate of construction cost. Design development. Continue regularly scheduled meetings. Attain additional information from the client to the consultants. Structural engineer to review codes and seismic conditions in a report. Mechanical and electrical to receive approvals from authorities having jurisdiction. Drawing coordination with all consultants and amongst themselves. Obtain cost estimates, Class C or Class B estimate. Prepare outline specifications. Construction documentation. Prepare a scope and schedule of all drawings with consultants, i.e. sheet size, scale, drawing standards. Coordination meetings continued. Check set review and progress drawing submissions. Final specifications and acceptable alternates. Unit pricing and cash allowances. Cross-coordination of all consultants. Revise and review. Update cost estimate, Class A. Submit to client for review, revise, and resubmit bidding and negotiation. Prepare addenda and coordinate a pre-bid meeting and site project tour. View alternates. Establish a schedule of values for charting the progress of construction. Contract administration. View shop drawings. Site meetings reports. Prepare site instructions, contemplated change orders, etc. Coordinate general reviews with consultants. View monthly progress billings with consultants. Takeover. Prepare deficiency lists and review warranty submissions. Prepare record drawings if required. 3.3.3 Coordinate the engineering systems documentation with the architectural documentation. 4.1 Understand the factors influencing cost. 4.1.1 Identify the factors influencing cost. Note the following typical fees for traditional phase services. Pre-design, i.e. functional programming, extra fee, schematic design. 12 to 18%, 12.5%. Design development, 12 to 18%, 12.5%. Construction documentation, 35 to 45%, 45%. Bidding and negotiation, 2.5 to 6.5%, 5%. Construction administration, 25 to 35%, 25%. Factors influencing cost. 1. Economical plus political. Inflation is a factor and should be included in the project budget. Market conditions, high demand, higher prices. Union or non-union labor during a recession, non-union labor drops. Interest, rates on financing costs. Political and social climate. Local, provincial, and federal politics play an important role in the financing of a project, as well as the timing of a project, especially during election periods when stability is lacking and prices can become erratic. 2. Environmental. Site characteristics, challenging topography, adjacent buildings, subsurface conditions, weather and season, winter protection costs. Location, dense urban areas versus remote areas. Travel distance to site, proximity to skilled labor, and disposal areas. 3. Building type and design. Simple wood frame versus steel or concrete construction. Code compliance. Building height and form. type-off finishes, feel life cycle of the structure, choice-off mechanical, electrical, structural systems. 4. Characteristics of the owner-client. Educated clients expect delivery below target costs, unnecessarily high standards of quality. Government clients have bureaucratic procedures. Uneducated clients need more time for decisions. 5. Type of construction project delivery. 6. Owner's timetable, i.e. meeting a very tight deadline. 7. Definition of project requirements. Functional program, the client may have a change of mind. External factors such as the development of new technologies or new legislation or inadequate research may all influence the costing of a project. One must, therefore, review the functional program or objectives. Ask the owner to clarify incomplete or unclear requirements before starting work design. Keep the owner full advised on the potential cost implications of any changes. For point 1.2, explain how these factors influence cost. Costs can be significantly higher if changes are made in the construction documentation stage when redesign costs and additional consulting fees arise. With respect to this fact, note that time and money can be wasted because of lack of appropriate direction from a client. 4.2.1 Critique the client's budget in conjunction with the program and the conditions for completing the project. For point 2.2, critique the recommendations made to a client following a value analysis. Value engineering determines the best or optimum value for investment in a construction budget. Architects work with cost consultants to compare trade-offs between design concepts, arrangements, materials and finishes, systems, construction techniques, and life cycle cost options. TSIS typically done in the schematic design phase. The result is lowered capital costs, which are always a consideration for clients. The objective is to minimize construction costs while maintaining quality, as well as adherence to the functional program. Developers and design builders are more interested in reducing capital spending than in life cycle cost savings. Meanwhile, landlords and building owners are concerned about reduced operating and maintenance costs and lower replacement costs. The architect should advise the owner by written comments and recommendations for all proposed substitutions made during the course of construction. Types of cost analysis. Embodied energy cost analysis assesses the environmental impact and energy consumption resulting from extraction, manufacture, delivery, installation, demolition, and recycling of building materials. The purpose of the analysis is to reduce embodied energy contained within all products used in construction. Life cycle cost analysis, used to evaluate the economic performance of a material or building system over the service life of the material or system. It includes all the costs associated with purchasing, installing, maintaining, and disposing of an item. All costs during the study period are discounted to convert future costs to their equivalent present values and account for the time value of the money. Life cycle assessment assesses the environmental performance of a product over its full life cycle, cradle to cradle. Performance is measured in terms of potential effects, such as fossil fuel depletion, global warming, and ozone depletion. Embodied effects are effects associated with making, transporting, using, and disposing of products. Meanwhile, embodied energy is associated with the extraction from and releases to nature. The essence of LCA is to cast a wide net across the relevant effects associated with a product, process, or system over its full life cycle. 4.3 Understand the various methods of estimating cost. 4.3.1 Describe the methods for estimating cost. Estimates. Classification of estimates. Class D estimate. 20% accuracy typically employed during the pre-design phase. The method is based on historic cost data for similar work. It is a rough order of magnitude of the total project cost, and it establishes an indicative estimate, often used for Treasury Board or capital investment approval. It is typically based on functional requirements. Class C estimate, 15% accuracy, typically employed during the schematic design phase or the end of the design concept stage, and is based upon user requirements, general description of the end-built works, preliminary site information and existing conditions, and production. Because of limited information, it has a high contingency value. Class B estimate, 10% accuracy, typically employed at the end of the design development phase when drawings and outline specifications are available. An expanded format is used, allowing for a reduced contingency. This method establishes a substantive estimate for Treasury Board approval. This estimate also makes allowance for all costs resulting from the anticipated schedule, expected market conditions, and suitable levels of contingencies. Class A estimate, 5% accuracy, typically based on the Class B estimate, and is submitted as a final pre-tender estimate at the end of construction documentation. It is based on specified project systems, a realistic construction schedule, and accurate labor and material costs. Types of estimating methods. Elemental cost uses the cost square foot for each element of the major building components, such as the structure or envelope. The cost framework is useful for the life of the project and is applicable to new or existing buildings. Relevant cost information can be applied from similar projects. Oh, the disadvantage of this method is that it is difficult to double-check without time-consuming analysis. The method doesn't use master format. It cuts across traditional construction trade areas, Class A, B, and C estimates. Area calculation, based on cost per square foot, used when providing general cost advice and for calculation of overall project cost. The architect should limit the use of this basic information and use only as a general guide at the pre-design stage. Oh, the advantage of this method is that historical data from many building types is available and useful. Furthermore, the concept is easily understood, applicable to all building types, and is straightforward to calculate. Oh, the disadvantage is that it doesn't account for unique conditions or special construction. It can also be misinterpreted as a result of its simplicity. Volume calculation, based on the cost per cubic foot. It is not a widely used method typically employed for specialized building types such as warehouses or multi-story buildings. It can be used as to double-check on other methods. However, the architect must ensure that historical data is comparable. Unit use calculation, based on the cost per bed or cost per seat, etc. This method uses very simplified historical data and is brief and to the point. It is relatively reliable, provided that the historical data is comparable. It is often used for preliminary budgeting. Oh, the advantage of this method is that it provides a quick reference or check at the early design stages. Oh, the disadvantage of the method is that projects are rarely identical. Careful adjustment must be made for differences. One must use this method with caution for preliminary advice only. One must clearly spell out qualifications and assumptions when information is released. One must not confuse unit use with unit cost. 4.4. Apply estimating methods within the framework of a project. 4.4.1. Identify the resources available to do a cost estimate. Data is most reliable when it comes from Canadian sources for estimating in Canada due to fluctuating currency. The resources available to conduct a cost estimate are reliable historical cost data, comparable projects, cost consultants and quantity surveyors, construction development experts such as construction managers, contractors, developers, construction price index data, published by government agencies and private companies, ExAC. 4.4.2 differentiate between the concepts of construction costs, project costs, and overall costs. Construction budget is the client's budget for the construction cost, the cost of the bricks and mortar, which includes contingencies for cost increases. Project budget is the client's estimated total expenditure for the entire project. It includes the construction budget, professional fees, costs of land, and right-of-way fees, as well as all other costs to the client for the budget, such as soft costs of insurance, legal fees, taxes, lawyers, specialty consultants. Overall costs, or total cost budget, includes the construction costs and first costs. This method includes the capital cost, initial cost of constructing the project, such as land purchases, operating costs, including servicing of the building, lighting, energy, insurance, and maintenance costs, includes repairs and renewals. The total cost is relevant to the long-term costs of owning and building an edifice. 4.4.3 use the preferred estimating method in a given situation. Theme 6, schematic design. 6.1 Understand the aspects of schematic design. 6.1.1 Identify the information required for schematic design given specific conditions. CHOP 2.3.5. The project program and requirements for the schematic design phase are as follows. Client objectives and constraints, especially the space planning requirements, legal surveys, geotechnical and soil composition reports, hazardous material information, utility information, including an environmental audit, construction procurement method, construction and budget milestones, any opinions of specialist consultants that will have an impact on the project. 6.1.2 Categorize the engineering services required for the schematic design of a given project, program, clients, and context. The engineering services required for the schematic design of a given project are structural, mechanical, and electrical design concepts and approach, estimating of probable costs, familiarity with the site and program. Note that early involvement by engineering consultants can lead to reduced capital costs and improved building performance. 6.1.3 Identify the documentation typically prepared for the client's approval of the schematic design. The following items are typically prepared for the client's approval of the schematic design: agreed upon design approach, program requirements, and schedule, including construction budget. Schematic design documents to illustrate the scale and character of the project, including OA site plan, O principal floor plans, O vertical sections, O building elevations, O illustrative sketches or perspective renderings, computer-generated or virtual reality presentations. O massing models, statement of probable construction costs with appropriate qualifications, effectively a Class C estimate. Summary of the status of design with respect to applicable environmental, planning plus zoning regulations and building codes. Description of structural, mechanical, and electrical systems. Basic area calculations and analyses. Site data, product and material description, and sample of key construction materials or finishes. 6.1.4 Explain the scope of building code analysis in schematic design. The scope of building code analysis in schematic design is as follows: a general overview of compliance with building code, fire department access, number of streets, detailed zoning information such as building setbacks, building heights, FSI or GFA to net ratios, as well as health and safety codes. In addition, accessibility impacts must be considered: barrier-free path of travel, accessible paths from parking lot to door, ramps and depressed curbs. Furthermore, the site plan must include the following applicable information: dimensions from property lines, the location of the proposed building, and the dimensions and locations of existing buildings, the existing and finished ground levels to an existing datum at or adjacent to the site, access routes for firefighting. 6.1.5 Explain the principles of sustainable design as they relate to schematic design. The principles of sustainable design that relate to the schematic design process include consideration of site selection, reduce site disturbance, building form, building materials, density, and open space versus building massing. 7.1 Understand aspects of design development. 7.1.1 Identify the information required for design development given specific conditions, CHOP 2.3.6. According to RAIC Document 6, the refinement of the design during the design development phase usually entails preparation of all architectural, structural, mechanical, and electrical designs, preparation of a comprehensive outline specification, Class C or B, additional review with authorities having jurisdiction, preparation of presentation documentation, such as drawings, models, computer renderings as agreed to in the client-architect agreement, Document 6, update of the construction cost estimate, update of the schedules for design, preparation of construction documents, and time frame for construction. During DD, all components must be finalized. Major revisions at a later stage will be costly to the architect and can result in compromises to the architectural design concept. During this phase, the client is responsible for the following: reviewing and commenting on the design, providing approval of the design, and authorizing the preparation of construction documents. Additionally, the architect is responsible for investigating various manufactured products for incorporation into the building, as defined by the functional program. Prior to making a final recommendation to the client, the architect should review the following factors: dependability of the source of supply, such as stability of the manufacturer or supplier and the types of warranties available, availability of technical data, samples, and literature on the product, performance criteria, including suitability for application and compatibility with other materials, durability and maintenance requirements, physical characteristics and availability of various colors, finishes, textures, or other features, fabrication and installation requirements, cost, time for delivery, past performance, comparative analysis with similar products in the marketplace. 7.1.2 categorize the engineering services required for the design development of a given project, program, clients, and context. The engineering services required for the DD phase of a given project, according to various consultants, are structural, based on the soils or geotechnical report, usually prepared at the pre-design stage, the selected schematic design, the future expansion and flexibility required of each space, restrictions regarding the locations of columns or other structural supports, defined areas including use, size, and finishes, fire separations, barriers, and fire ratings, these eyes and location of openings, construction materials, the method of construction delivery, and expected time frame, leading to the resolution of design issues such as typical bay framing, including typical sizes of beams and columns, maximum depths of members, and all critical sizes of members, size and location of openings through the structure for all work by other disciplines, identification of items to be embedded into the structure, requirements regarding fire ratings and fire separations, provisions for special equipment and typical mechanical equipment, including window washing equipment, mechanical rooftop units, self-leveling docks, chimneys, slab depressions, etc. Mechanical, based on future expansion and future changes to the building to allow for flexibility of mechanical systems, wall and roof construction, window sizes, type of glazing, and type of window coverings, hours of use of the building, allowable variation in room temperatures and humidity, areas requiring special treatment for air conditioning, fire protection, plumbing, noise, etc., fire separation and barriers, requirements for special controls and energy management, analysis of water and special waste removal equipment, other special equipment such as lawn sprinkling systems, leading to the resolution of design issues such as central versus individual heating and cooling plants, taipan size of air conditioning equipment, taipan size of the heating system, special HVAC systems such as heat recovery systems and heat pumps, size and location of major ducts and pipes, location and approximate size of all mechanical equipment, other features such as noise control, vibration dampers, special controls, electrical, based on the selected schematic design. Information in all areas, including function, size, finish, and materials, as well as lighting levels, the future expansion and flexibility required for each space, the method of construction project delivery, and expected time frame, leading to the resolution of design issues such as the anticipated electrical load and allowances for future expansion, requirements of incoming electrical services and any space requirements for a vault or substation, the distribution of power and utilization voltages, locations for electrical closets, communications rooms, bus duct risers, requirements for embedding conduits, light fixture selection and requirements for ceiling systems and ceiling space, telecommunications and data systems, fire alarm systems, PA systems, intercoms, and security. Manufacturers of various building systems, such as elevator companies and suppliers of wall cladding systems, will also need to be consulted. 7.1.3. Identify the documentation typically prepared for the client's approval of the design development. The documentation typically prepared for the client's approval of the design development includes drawings which illustrate planning, appearance, and construction assembly of the project, site plan plans, elevations, sections, a project brief detailing area calculations, building systems, outline specifications, code analysis, revised construction cost estimate, effectively a Class C or Class B estimate. 7.1.4 describe the impacts of universal accessibility on design development. The impacts of universal accessibility on design development include the development of detailed analyses of compliance with the building code, including an awareness of details and content, which facilitates the approvals process, defined occupant loads, building classification and existing strategies, accessible washroom requirements, areas of refuge, exiting requirements. 7.1.5 explain the principles of sustainable design as they relate to design development. Site design, site selection. Include all stakeholders in the site selection process.